Hey, Algebra 2! Hope you guys are having a great day. We are moving on to 3.7 today. There's 2 days in 3.7. And we're basically going to be talking about how to use all of these things that we've learned in Chapter 3 to start graphing polynomials without a graphing calculator. So, first we're going to talk about what end behavior means and what that is going to look like with a polynomial. And then we're going to look at, in order to graph, which will be tomorrow, excuse me, we'll need end behavior, intercepts, zeros, and multiplicity of zeros so that you can effectively sketch. I mean, it's not going to be a perfect, accurate graph, but that's okay. It's a sketch, but it should include all of these things. So, end behavior, right? Basically, a polynomial of any degree, it's as x gets really, really, really big. So visually, right, if I make a graph, right, as x gets really, really big, so that means like 5 million on the x-axis, right, the graph will at some point only do one thing. It will either go up forever or it will go down forever. And similarly, on the negative side of the axis, right, as x gets super, super, super big negative numbers, becomes a super big negative number, so like negative 5 million, and even bigger than that, or smaller than that, however you look at it, the graph will, at some point, only do one thing. It will either go all up forever, or it will go down forever. And so that's kind of what end behavior means. It's like, as x gets really, really big, or really, really negative, does it go up? Does it go down? And, you know, what's happening? Do both ends go up? Do both ends go down? Does one up and one down, or is it this way? Right, so we've got like all these things happening on the ends. So that is what end behavior really conceptually means. Okay. Once you get to pre-calc and calculus, you'll talk more about limits, and you'll talk about what that actually means in this case. But for now, we just want to know like what end behavior really means and how to determine what it looks like on a polynomial. And so one of the ways to write that as x gets really, 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 really big is this x arrow positive infinity, right? That basically means as x approaches positive infinity, or as x gets really, 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 really big. And then on the other side, we have as x approaches negative infinity. So as x gets really, 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 really negative. So we're going to use that notation in the future. So just wanted to give you a heads up that that's what that means. Okay? And this depends only, or your leading behavior depends only on your leading term. Okay? Because in the long run, this gets more conceptual too, but in the long run, right, if I have like a an x to the 7th minus 2x to the 5th plus 3x squared minus 1, and that's my function f of x, right? As x gets really, 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 really big, or really, 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 really small, really, really negative, the term that's going to like dominate is the leading term, this x to the 7th. That determines the behavior on the extremes, because when you plug in really big values of x, so say I plug in 5 million here, raise that to the 7th power, that's going to be like be more, what's the word I want? It's like, it's stronger than 5 million to the 5th, right? Or 5 million squared. So like, as x gets really, really big, these other numbers and those other x's don't really count as much. you know, they determine like the specific value, but this, the leading term, determines the big picture behavior, right? The end behavior. So when you are trying to determine end behavior, you only need to look at the leading term. So if you have a polynomial and you're looking at the leading term, right, you want to look at two things. First, look at the degree. Is the degree even or odd? Now, an even degree, like x squared, x to the 4th, x to the 256th, right? All of those are even degrees. All of those are going to behave similar to x squared in the long run, okay? So x squared looks like this. Yeah? Well, ish. And negative x squared looks like this. Ah! I'm so like discombobulated. Okay, so you either have up, it's goalposts, right? Goalposts or downward facing goalposts. Okay, and so that's if it's an even degree. You'll have one of those two things. So both ends do the same thing. If it's an odd degree, it's going to look more similar to a cubic, right? It's going to behave like a third, in the long run, it's going to behave like a third degree polynomial. So you'll have one side go up and one side go down, or you'll have the other direction. Okay, one side up or one side down. And the which way depends on whether or not there's a negative in front. So anyways, that's what you want to look for. You look at your degree. Even degree, you've got goalposts or goal. And odd degree, you've got like, I don't know, that. Okay, so those are your possibilities based on the degree. Now in addition, you want to look at whether or not the coefficient is positive or negative. This is the leading coefficient. If it's a positive coefficient, then it'll look like the positive x squared or the positive x cubed, right? Remember, your positive x squared on the ends looks like that, and your positive x cubed on the ends looks like that. So if it's a positive coefficient, you have one of those two situations. And if it's a negative coefficient, then you have the opposite, right? You have them both down, or you have the left up and the right down, okay? So I'm going to make a nice little box to kind of keep that organized, and then I'll show you the algebraic notation in order to be able to write it down. So I just wrote our degrees up here, and then our coefficients, whether or not they're positive or negative, here. So if it's an even degree, and a positive coefficient, so we're in this first box here, right? Even degree means it looks like an x squared on the ends. And since it's positive, it's going to look like a positive x squared, so like this. So your end behavior looks like that, okay? Now, the way we write this algebraically is that we have to write it, we say something like this. As, I'm going to make it smaller later, but as x approaches positive infinity, f of x, or the polynomial, whatever it is, approaches positive infinity. Okay, and basically what that means is as I make my x go further and further to the right, as I make x really, really big, my function f of x, which is y, also goes up, okay? And so you end up with an end behavior that looks like that, okay? Then you also have to describe the left side. So that's as x goes to negative infinity, f of x also goes to positive infinity, because now as we're going in the negative direction, negative x direction, we want f of x, or y, to also go in a positive direction. Okay, so that's what that looks like. And so now we do an odd degree but a positive coefficient. That's going to look like a regular x cubed function, which goes up on the positive x axis and down on the negative x-axis. Okay, so you would write that as x approaches positive infinity, f of x goes to positive infinity. But as x goes to negative infinity, so as you go to the left, f of x decreases, it goes down. Okay, so f of x approaches negative infinity. So the only thing that's different there is what I highlighted, right, is this negative, is that as x goes to negative infinity, instead of it going to positive infinity, which means it goes up on the left, it goes down on the left. Okay, so now go ahead, fill out the other two boxes and check your answers with what I write. So for a negative coefficient even degree, you should have down, and then you just flip-flop your odd degree behavior for the negative coefficient. Okay, because it's just a reflection over the x-axis, which makes sense, right? Throwing a negative in front of your leading coefficient, your leading term. Okay. So let's go ahead, try the next couple problems on your own. So determine the end behavior of the following polynomials. So go ahead, try them, pause. Okay, so the only thing we need to look at is the leading coefficient, or in the leading term. So the degree of the leading term and leading coefficient. And so this one is an odd degree, and it's got a positive coefficient. So that means we're looking like a positive x cubed on the ends. So it looks like that. Next one is an odd degree, but a negative coefficient. So that's going to be the flip-flop of that. So the next one's going to be up on the left, down on the right. H of x is an even degree and positive. So that one's going to look like this, up and up. And the last one is even but negative, so we go down and down. And I'm also going to write the algebraic notation in there just so you get practice with that. All right, so go ahead, check your answers for these. And then let's move on to the next page. All right, intercepts. Intercepts are super important. They're pretty, we've been working with them for a long time, so it shouldn't be that big of a deal. Y-intercepts are really simple, right? It's where it crosses the x-axis, which is when x is equal to 0. So you want to set x equal to 0 and just solve for y, or what f of x equals, okay? So for example, find the y-intercept of the following function. Well, when x equals 0, f of x equals 0, then I have 0 to the 5th minus 0 to the 4th, blah, 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 plus 16. Right? So my y-intercept, in this case, is 16. If it's in factored form, you can still do the same thing, still just plug in x equals 0, you just have to multiply some numbers together. Okay? The x-intercept's a little more difficult, right? If it's not already in factored form, you have to factor it, or you have to find the zeros with synthetic division, or use the irrational root theorem, and so that gets a little nastier. But you've done it, you know how to do it. Right? It's when you set y equal to 0, and then you have to either factor by grouping, use synthetic division, whatever it may be, right? And then find the zeros. Just like we have always done, okay? And then now at least you have some information, right? You know whether it goes up or down, and you know what the intercepts are. And then you can connect the dots, essentially, right? If you have that information. Okay. The last thing you need is the multiplicity of each zero, of each x-intercept, because what you can have, on a graph of a polynomial, you can have like the function like bounce off the x-axis or go straight through. There's a bounce and there's a straight through. And that depends on the multiplicity, which I'll talk about in the next video. So just a refresher of multiplicity, right? Say we have the function, it's already in factored form. Find the multiplicity of each intercept. Well, the first one, x minus 4 to the third, has multiplicity, right? It's how many times you can divide that out. So x equals 4 has a zero of multiplicity 3. x equals 1 is multiplicity 1, because there's a first degree there, and x equals 2 has multiplicity 4.